Hello, welcome to grade 12 physics, and here I'm going to be your teacher, Mr. Fernando or Mr. Morales, whatever you want to call me, and I'm going to help you with your grade 12 physics course, which is a very challenging course. So I'm making a few videos to help you out with the homework questions, but please feel free to ask me any questions that you may have in the comments or request particular questions so I can make a video for you. And I hope that you're going to subscribe to my videos, that way you're going to get the best learning possible for your grade 12 course. And let's get started from the Nelson textbook. We're going to be looking at section 1.1, question number 1. So here we have a cardinal flies east for 2.9 seconds in a horizontal plane for a distance of 22 meters from a fence post to a bush. It then flies north another 11 meters to a bird feeder for 1.5 seconds. So if you're not familiar with my grade 11 course, and in that I show you the problem solving method in full detail, so here I'm going to go with the same steps but a little bit more faster. So the first thing that we want to do is to try to visualize the problem. So let's draw a cardinal. And this cardinal, they tell us that it's flying east for a distance of 22 meters. So the first displacement that it undergoes is going to be directly to the right, which we take it to be east. So the first displacement, we're going to use the notation delta D1, and it has a magnitude of 22 meters. The direction is east. Then the second displacement, the cardinal flies north. So I'm going to make north pointing up. And this is our second displacement vector, which has a magnitude of 11 meters, and the direction is north. So recall, because we're dealing with vector quantities, you have to state both the magnitude and direction. So that's why here we have the scalar portion with the direction as well. And make sure you put the hats on top to show that it's a vector quantity. And the other piece of information that they give us is the time that each displacement takes. The first displacement takes a time interval, so we write delta T1, 2.9 seconds. The second displacement, which when it was going north, delta T2, took 1.5 seconds. So this is all the information that we have. Now, what are they asking us to calculate? The first thing they want us to calculate is the total distance traveled. So total distance, we're going to find delta dt. So this is the notation that we use for distance travel. Total, that's where the t comes in. But keep in mind that since they're looking for the total distance traveled, this is actually a scalar quantity. And because it is a scalar quantity, there's no direction. So that's why if you look at the quantity here, there's no arrow hat. There's no arrow hat. So no arrow hat. Now, if we want to calculate the total distance traveled, all we have to do is add up all of the individual displacements. But we're only adding up the scalar portion of it, so the magnitudes. So let's try to write this out. So the sum of scalar part of displacements. Now we can write an expression for this, and we can write as delta d total, so the total distance traveled is the sum of the first displacement plus the second displacement length. So this is a very easy, because we're just going to be adding up scalar quantities, which is just adding up the numbers as you will with math, you will. So 22 meters plus 11 meters, so the total displacement is 33 meters. Okay, not so bad, right? You're like, physics 12 is not so hard, but just keep in mind this is question 1, but I kid you not, it's actually really hard. So stay tuned and then you're going to see the next part. But again, if you're enjoying the video, make sure you hit subscribe, and that way you're going to watch more videos and learn from me. So let's see what part B asks us to find. To calculate the cardinal's average speed. So the notation that we use for average speed is V average. So average speed. And when we use the word speed in physics, we want to try to distinguish it from velocity. So that's what this question is asking you. So the average speed is trying to look at the scalar part. And again, what do we mean by no scalar? There's no arrowhead, so it's not a vector quantity. And the way we're going to calculate this, the average speed, is the total distance traveled over the total time interval. So one way you can write that is total length over total time. But since in part A we already found the total displacement, the distance traveled in that case, the total displacement scalar part, which is the distance traveled, we can put that value in from before. So the average speed is going to be 33 meters. And the only part that we need to find now is going to be the total time. So remember they gave us the time for each interval. So let's look from before, and we have the first interval and the second interval. So we're going to do delta t1 plus delta t2. So 33 meters for the distance traveled, and what was it, 2.9 and 1.5. So I'm not so good at the calculation part, so that's why I'm going to use the calculator now. So 2.9 plus 1.5, 4.4. So one way to interpret this is that this cardinal is able to cover 33 meters for every 4.4 seconds. But if you wanted to describe it differently, you can actually reduce the ratio. So this would be 7.5 meters per second. So this is much easier to interpret, because this means the cardinal travels 7.5 meters in each second of time. So that's going to be our average speed. Now there is part C. This is the part that you should stay tuned, so don't run away yet. It's not so easy. This is actually the hard one. So for part C, they want us to calculate the cardinal's average velocity. Now for the average velocity, the notation that we have is V average, but that's the same thing as the average speed. But to distinguish it, because this is actually a vector quantity, you need to include the arrowhead on top. So average velocity. And this one here is a vector quantity. So this means that it has an arrowhead. But let's look at the formula for average velocity. It's just going to be the total displacement divided by the total time. So in this case, we have total displacement. Over the total time. So this is different from before, because before it was the total distance traveled, and that was a scalar quantity. Now we have total displacement, which is a vector quantity. So the total displacement is the sum of the individual displacements. So in this case, we have delta d1 plus delta d2. And remember, our total time was delta t1 plus delta t2. And I think it was 4.4 seconds, so let's write that in. Let me just go quickly double check. Yeah, 4.4 seconds. But the more interesting part is the top part here, so that's where I want our attention to go towards. Our total displacement is the sum of the individual displacements, delta d1 plus delta d2. And that's how we're going to calculate the average velocity. So in order to do that, we need to actually calculate delta dt. So we're going to take a mathematical aside and do this separately. So the total displacement is the sum of the individual displacements. Now this is vector quantity, so we have to do vector addition. So this is what makes physics hard. We have to use vectors. So vector addition. Now to perform vector addition, let's do some quick recap from grade 11. So to do vector addition, we're going to use the head to tail method. So what does this mean? The head of the first vector is attached to the tail of the second vector. Now for vector addition, it doesn't matter which one you take to be the first vector or the second vector. It can work either way, so it's going to give you the same result. But for simplicity, let's keep in mind that this is going to be the first vector, delta d1, and our second vector is delta d2. So if we follow this vector addition of head to tail, we're going to have to use our previous diagram. And luckily for us, look at the two vectors. How are they attached already? They're already attached head to tail. So the only thing that we have left to do is to draw the resultant. So the resultant is drawn from the tail of the first vector to the head of the second one. And we call that the total displacement vector, delta dt. That's our unknown. Now to calculate this, what we do, we're going to take advantage of something. We're going to take advantage that this is, in particular, a right angle triangle. And this means that for this right angle triangle, we have the two sides. We have delta d1 and delta d2. So to find the third side of the triangle, we can take advantage that is a right angle one, which means it's at 90 degrees. And we're going to use the Pythagoras theorem to find the unknown. So recall, what is the Pythagoras theorem? We have c squared equals to a squared plus b squared. where C is the longest side of the triangle, the hypotenuse, and A and B are the other two sides. So if we use our notation from the diagram, we have delta dt square equals to delta d1 square plus delta d2 square. And to isolate for the total displacement, we take the square root on both sides. And at this point, it just becomes a matter of substituting in the values. So that's going to be 22 square plus 11 square. Let's see what we get. Please correct me if I'm wrong, but I'm pretty sure I won't be wrong. This is about 24.6 meters, right? Because the distance was the scalar quantity. I mean a length, so it's in meters. So the length of our total displacement is 24.6. But if you're clever, you will have noticed something. Pythagoras is working for sides of a triangle, which are scalar quantities because they're length. So notice that I dropped the arrowheads. So this total displacement is actually only the scalar part. But look at my drawing. Total displacement is a vector quantity. So what does that mean? We're missing something. So what do we know about vectors to be true? Vectors have both a magnitude and direction. So that's right. We are not finished yet, because to find the actual vector, you need to also find the direction. So what do we mean by direction? It's going to be the angle that the vector makes relative to the horizontal, which is either the x-axis. So let's call this theta. And this theta, we're going to take it relative to the horizontal. So whenever in physics, whenever we say that, that means relative to the x-axis, or closer to the x-axis. But again, we're going to take advantage of something that we figured out before, that this is a right angle triangle. So whenever you have a right angle triangle, you can use the famous acronym SOHCAHTOA, which means sine, cosine, and tangent ratios. So let's use tan. That's my preferred one when trying to find directions. It's always use tan ratio. Tan theta, which is opposite over adjacent. So by looking at the angle theta, the opposite side is 11 meters and the adjacent side is 22. So let's take the tan inverse. Okay, let's calculate this. Which is about 27 degrees. Good. So we needed to find the direction and the magnitude in order to fully describe the total displacement, and now we can write it as a single expression. So our total displacement is 24.6 meters. And the direction, because I made it closest to the horizontal, if you start off east, you have to rotate 27 degrees north to get this. You might want to look at my grade 11 videos, and that way you can get more examples on how to find the directions. But I don't want to take up more time. It's already been almost 20 minutes. So let's finish this question. Alright, so we're not finished this question because we want to find the average velocity. So to find the average velocity, we said it was the displacement, the total displacement divided by the total time. And we found the total displacement to be 24.6 meters east, 27 degrees north. And we're going to divide this by 4.4 seconds. So the average velocity is going to be about 5.6 meters per second. The direction, east, 27 degrees north. So the main idea to take away from here is the total distance traveled is a scalar quantity, and it's just the length of the path that you actually travel, which is the sum of the scalar parts of displacement. For the average speed, you're looking at the total length over the total time, and that's a scalar quantity. But when you find the average velocity, that's going to be a vector, so that's going to be the total displacement over the total time. So to find the total displacement, you may have to do vector addition, but don't forget that you also need the direction. So that's how you find the average velocity. Welcome to grade 12, and I'll see you in my next video, so I'm going to be looking at the other questions from this section. So please hit subscribe, and that way you'll get to see the rest of them. Until next one, bye bye.